Well, hello and welcome YouTube. Mr. Robbins back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on aside as we jump into the Chapter 3 review in the Big Ideas Math Integrated Math 1 textbook. This is on all things graphing, linear functions, linear equations, etc. Now, the early part of the chapter, sections 3.1 to 3.3, the same one we did the quiz review on, I did slow down and we talked about what's a function versus what's not a function, what's linear versus non-linear, independent, dependent variables, domain versus range, continuous versus discrete, what is function notation. A lot of things were done there, as well as doing some graphs. Now, we plugged points into x, got values out for y, and then we plotted them and graphed. But then the next part of the chapter, sections 3, 4, 3, 5, 3, 6, we graphed out a standard form and slope-intercept form without use of a table. And then we transformed graphs of linear functions. Now, that was section 3.6, and it is a little overloaded here. For 28 questions that we have in this review, 7 of those 28, a quarter of them, are out of that last section. And I know that there are a lot of people that maybe don't necessarily cover that. So we'll do what we can with it, obviously, right? We'll talk about it. But if you don't get those problems covered, you still have numbers 1 through 21 going for you. Now, we will have examples going through each section. I'll lay them out. We're going to go ahead and get started. If you want to jump to the description section down below, you can download this PDF of this stuff here. We might not graph in the early on portions of it, but I'll provide graph paper for the later sections that we do have. Without further ado, I'm going to go ahead and get started. We are going to look at section 3.1 on functions. Now, here we have a table. I'm going to call this out before I actually do the problem. We have a table here, and I see number 1, I have a list of ordered pairs. Number 2, I have a graph. Number 3, I have a mapping diagram. These are 3 different representations, and number 4, I have an equation. But I have 4 different representations here, right here, and with each of them, we can determine whether it is a function. Now, the example one that they give is in the table itself. And in the table, what we're going to seek is there a repeat in our input value x? And if there's a repeat, is there a different value y given that input? So when we input 2, we output 5. That's an ordered pair like 2, 5, almost like this is 0, 1. Know what I mean? And 5, 11, 7, 19, 9, 12, and 14, 3. That's why we're looking for a repeat on x. It is not a function if you have the same x and different y values for that same x. This one doesn't seem to have a repeat on x. Every input has exactly one output. Therefore, this is indeed a function. Now, each different kind of representation might have a different kind of test for whether something's a function or not. It's all based on whether the input has more than one output, but it's not always looking for repeats. Now, on number 1, as we get started, we are looking for repeats again, because this set of ordered pairs would be the same as a table. We have the inputs of 0 and 5 and 7. No repeats on x. And listen, y's can repeat, although they don't. Y's here can repeat, but they're asking whether or not it's a function. It is a function. No x's repeat means there's no chance for multiple outputs for the same input. So function, let's see, how do they say it? Every input has exactly one output. I'll be ready to say that for anything else that is a function. So I'll copy that just in case I got to paste it. Number 2, we have a graph this time. Now, how do you see repeats for x on a graph? Well, you're looking for, again, multiple y values for the same x. Now, what you can do is something called the vertical line test. I get to scan my vertical line, but with this vertical line, we can determine, is there ever a vertical line that will cross through 2 points of your relation? If I go through at x equals 2 right here, it only happens to hit this 1 point right there. So far, it's passing the vertical line test. So far, it's a function. But then I scan anywhere over here, including right here, or a little farther out, just to be distinguishing. These 2 points are hit. Multiple y values are hit for that x value. I don't know what that is. X is negative 1.2 or something like that. And there's a y value of around 2 and y value of around negative 1.1. The point is there are 2 different y values for that same x value. Anywhere when I go to the left of x equals 2, it is failing the vertical line test. There are multiple x's for the same, there are multiple y's for the same x. And because there are multiple y's for the same x, it is not a function. There are multiple outputs for the same input. So not a function. Based on the vertical line test, maybe you can just say it fails the vertical line test or it doesn't pass it. But based on the vertical line test, there are 2 inputs. There are 2 I keep saying that. There are 2 outputs for any one input. For every input, for any x value that is less than 2. Now, that is the most overly descriptive version of not a function, not one for which I'll state in any other problem type. especially when we hit the chapter 3 test and stuff like that. But I want to just describe that one because guess what? Vertical line test wasn't on the quiz. So I wanted to make sure that quiz review. So I want to make sure this was hit here. Mapping diagram was also not on the quiz. So let's look at number 3. In a mapping diagram, what you'll have is you'll never see repeats. You can see this shows X and this shows Y, but it's less X and Y and it's more domain and range. Domain and range don't repeat themselves in lists, and these won't either. Here's your domain, here's your range. What X values exist, because they don't repeat, you're not looking for repeats. You're looking for whether any input maps to multiple outputs. Now, we would see that through arrows. When you see this arrow go from 11 to 7, that means there's a point on your graph that's 11, 7. Does 11 go to any other Y value? No, it doesn't. It doesn't go to the 8. 15 exclusively goes to 8. That means there's a point 15, 8, and 22 goes to 7. Now, as I stated before, you can repeat Y values. You can have the same output from 2 different inputs. You can't have the same input have 2 different outputs. So none of 11, 15, or 22 are branching out to both outputs. Like, it's not like 22 is going to both 7 and 8, because then that would be 22, 7 and 22, 8, same input, different outputs. Therefore, this thing is a function. So on number 3, we do have a function. Every input has exactly 1 output. I can copy and paste what we said that first time like that. Okay, few of them are functions. The vertical line test was not. Let's go move forward to, we still have another question on the set. The function, this time they tell you it's a function. It's not a question of whether it is. So on number 4, the function y equals 10x plus 100 represents the amount of y in dollars of money in your bank account after you babysit for X hours. So to me, it looks like I already have $100 in my bank account, and then I'm making $10 an hour babysitting because for my X hours there. And then I put it in my bank account there for Y. It says identify the independent and dependent variables. So part A, the independent variable is X, which is the amount of hours you're babysitting. And the dependent variable is Y, the amount of money that you have in your account. Dollars. So the reason for this is because the amount of dollars depends on the amount of hours that you babysit, not the other way around. I mean, that's in a situational case, but also it's in your equation. Y is all by itself. Y will be evaluated based on what you substitute for X. And that's kind of what we're expecting to do. We treat X as input, Y as output. That's how it's going to roll. For the most part, if X and Y are your variables, X will be independent, Y will be dependent. And for the most part, when you have time involved, time will be an independent source. We haven't yet seen time as a dependent source. I'm not saying it can't be. We just haven't seen it. Part B, you babysit for 4 hours. Find the domain and range of the function. So it says you babysit for 4 hours. A part they're not mentioning is continuous versus discrete. I think because they didn't describe it here yet, but I'm going to talk about it. Your time, to me, personally, and I don't know if this is the way that they're going to wager this or not, but to me, your time is a continuous flow. Meaning, if I babysit for half of an hour, I will be paid for half of that hour's wage. Instead of $10 for the hour, I'll be paid for the $5, which means I'm paid for my fractions of my time as well. So my domain to me is all of the time that I babysit, all of the time from 0 to 4. The domain is not 4. I have values for X up to 4 from 0, time 0 when I start onward. Now my range is based on my lowest amount of money that I made or that I have in my account, I should say, at hour 0, up to the amount of money I have at hour 4. Now, we should know, based on that, we should know these days after we learned a lot of more things on slope-intercept form, that when you look at when X equals 0, you're going to get 100. That'll be that value, the constant. But then when I substitute 4 into here, I get 40 plus 100, which is 140. So after 4 hours of babysitting, I will now have $140 in my account, but I started with 0. So my range of values from the time I started babysitting to the time I finished babysitting went from $100 on Y all the way up to, I was going to say $400, all the way up to $140. This is my domain, this is my range. Now, it's because it was a continuous relation, not a gap for just hour 1 and hour 2 and hour 3, etc. It's because of this that we wrote these as a compound inequality set, not as a list of numbers. It's not that just after hour 1 it's 110, after hour 2 it's 120 like that. We get paid the fractional amounts as well, even cents on the dollar, I suppose. Okay, Section 3.2. Section 3.2 is on linear functions. This time we know that they're always functions and all that, but now we're trying to determine whether or not they're linear sometimes. And that's actually what some of these examples show. Does the table or equation represent a linear or nonlinear function? Explain. Now the first one in this table, what we're going to look for is as x increases by a constant amount, and it is, they're showing that they add 4 each time, do the y's increase by a constant amount? If so, that would be indicative of a linear function. Here, x is added by 4 each time, but the y's, and they don't need to add by 4 each time, but they need to add by a constant. Y adds by 4 from 5 to 9, then plus 5 from 9 to 14, and plus 6 from 14 to 20. It's not to say there's not a pattern. There's absolutely a pattern, and I expect the next time I'm going to add 7 and get 27. But that's not linear. That's just a, it's a little growth over time. That's not a line, if I graphed this thing. So as x increases by 4, y increases by different amounts. The rate of change is not constant, so the function is non-linear. It needs to be a constant change. Constant change to be linear. This is not. This next one is y equals 3x minus 4. They say the equation is in the form y equals mx plus b, so it's linear, and they're not wrong. If we can rewrite an equation in the form y equals mx plus b, which we should now, if you're in the review, you should now know from section 3.5 is called a slope-intercept form. If you can rewrite an equation in slope-intercept form, you have a linear function. Heck, section 3.4, we learned standard form, that ax plus by equals c. If you can rewrite it in that form, you have a linear function. So based on those two things, yeah, we do have one. Now, what are the criteria for us? What we kind of said was x and y can't be multiplied together. They can't exist in exponents or in denominators of their equations. They need to be raised to the first power. And y absolutely has to exist. X might not need to exist, but y absolutely does. Those are things to make sure that you have a linear function, for sure. Now, numbers 5 and 6 are the other two. Actually, no, I take it back. Number 5 is still a table. So number 5 asks if we have a linear or nonlinear function here. Because last time was nonlinear, I'm kind of hoping this one will be linear. So we'll see. What we're looking for, again, is based on x having a constant rate of change, which it seems to, we're adding 5 each time. Gone are the days of just adding 1 each time. Maybe, maybe, maybe. What's happening with y? 2 minus 3 is negative 1. Negative 1 minus 3 is negative 4. Negative 4 minus 3 is negative 7. We're constantly changing y by minus 3 each time x is constantly changing by plus 5. Because of that, this is a constant rate of change. If it's a constant rate of change, this is linear function. I don't want to say that word. It has a constant rate of change on both y and x simultaneously. All right, number 6 is a graph, and they're not asking whether it's a function, although if they were, it would be a function. It passes the vertical line test. But is it linear? The real question on number 6 is, does it make a line? It does not make a line. No, this is not a linear function because it doesn't make a line. Not a linear function. The graph is not a line. It's a function, but it's non-linear. Okay, so the whole point is it's not linear. Okay. Number 7, not asking about whether it's linear or non-linear. They're actually giving you an equation that is, I'm going to rewrite it in slope-intercept form to show you that it's a linear function. It's pretty much there. And that was the point I wanted to make on the thing where they said the equation's in the form y equals mx plus b. Well, if you can get it in that form, it's linear. It doesn't have to start in that form. This is kind of in that form. I'd have to write negative 8x plus 60. Hey, I can write it in the form. This is a linear function, right? Okay, so here we go. The function y equals 60 minus 8x represents the amount y in dollars of money you have after buying x movie tickets. So before I ask and answer parts A and B, we're looking at, to me, we have $60, and then we spend $8 on every movie ticket, on X movie tickets, and that represents how much money we'll have left ultimately. Part A, find the domain of the function. Is the domain discrete or continuous? So this is where they started to bring up discrete versus continuous, and it's weird that they ask it last. We're either buying the movie ticket or we're not. We can't buy half a movie ticket, that kind of thing. So it's not continuous. This is discrete. This is discrete. Movie ticket purchases must be in full. Movie tickets are whole amounts. Anything like that. Specifically, they're asking about, is the domain discrete or continuous? And the number of movie tickets are the domain. So movie tickets are whole amounts there for that. Now they ask for finding the domain of the function. The domain asks how many movie tickets, and this is something we can kind of do two things in one with this because they are going to ask us to graph. So what I'm going to do right here, guys, is I'm going to make an XY table, but they're asking basically how many movie tickets can we afford? How many movie tickets can we afford? And based on that, we can come up with domain and such. I can purchase 0 movie tickets and still have my $60. Now, if you notice, we decline, we lose $8 every time we purchase a movie ticket. So instead of doing the math each time, let's just do 60 minus 8, and we get 52. And then a second movie ticket is 52 minus 8, which is 44. And then we have 36. Subtract 8 again, we have 28. Now, these are not multiples of 8, so this will be an interesting concept as far as where we finish, what we get to. This is 20. Minus 8 is 12. Minus 8 is 4. 4 minus 8 is a negative number. So I'd be owing the movie theater some more money, in some sort of way. I don't have enough money for an 8th movie ticket. Because it's discrete, we wouldn't connect these dots on a graph, which we are going to graph. But this represents our domain from 0 to 7. These values would represent the range. They're only asking about the domain, though. So when it comes to domain, we would write that list of number of movie tickets we can purchase. It's not 0 through 7. It's the list of these whole number amounts. So unlike the question on the time with babysitter, babysitter time, all that stuff, we don't say X is between 0 and 7. We actually have to write all the different numbers. So that's your domain. That is part A, and it's discrete. Part B asks you to graph the function. Now, I'm doing it based on plugging these numbers in. That was kind of our way of going about it here. And based off this, too, we also have to, first of all, have to get a graph. Let's copy and paste. We also have to change our scale. Change our scale on Y. Now, our X's seem fine. We're going from 0 to 7. But Y, since we're going all the way up to 60, we might want to go by amounts of, if I went by 8s, it would actually be good, except they would be right in between numbers. I don't mind it. It'll just look a little weird, but we're going to go by 8s. So this is, 8, 16, 24, 32, 40. And then this goes all the way up to 80 right here. Now 60 is right in between 40 and 80 right here. Oh, I don't know. This might not be perfect here. I was thinking that at 10 we would hit 64. I was misrepresenting what we had. Either way, I'm going to do it. Let's get it done. So we have a point right here that's 0, 60. And then 1, 52. Here's 50. Oh, wait. I said I'd go by 8s. Hold on a second. What did I do here? That's not 60. That's not 60. What's 60? This is 48, 56, 60, between 60 and 64. Got it. Okay. Now I'm doing what I thought I'd be doing here. Every point is going to be exactly halfway between any of these multiples of 8. So when I subtract 8, remember these go by 8s. So minus 8 is another half down here. Here's 1, 52. 52 is right in between 48 and 56. So it's right there. So all these points, guys, are going to go at these halfway marks. And honestly, that's fine. This kind of helps remind you that you're not going to hit this x-axis. You were a fractional amount of a movie ticket short of being able to spend all your money, potentially. And that's also why we're not going to, draw a line through this or anything else. It's not an all real number domain. You definitely can't purchase negative amounts of movie tickets, and you can't have negative amounts of money, and you can't have fractional amounts of movie tickets. So this would be the graph here. Remember, these scales still go by 1, so that's 5 and that's 10. We can afford up to 7 of them, and those are the different values we have. So there we have it. That is part B. Okay, and that is section 3.2. Let's move forward. Let me get some water here. Okay, section 3.3 was on function notation, and we've been using it moving forward as well, so hopefully we're starting to feel a lot better about it. Function notation is this right here, this f of x. It's the same thing as saying y. Of course, you don't need to say f of x. You could also say g of x, r of x, h of x, k of x, all these different kinds of things. We default to f, maybe because it's, function starts with f. But there are other ways of saying y, and we can do more with it. Number one, it can represent a function. Number two, using other letters like g of x and stuff can say these are different y values that we have, different y graphs. Number three, when we do something like this, f of 2, which doesn't say f times 2, by the way, It means we can substitute 2 for x and get the y value out. It's a quicker way of saying what is y when x equals 2, just by saying f of 2 equals. And we could do that here. So for their example, they said evaluate this when x equals 2, so we get to do f of 2, boom, because they could have said find f of 2. 3 times 2, that's your substitution, minus 9. And you don't do anything on this side. This is just y equals, y equals, y equals. 3 times 2 is 6. 6 minus 9 is negative 3. So f of 2 equals negative 3, which means when x is 2, y is negative 3. That means you could plot that point on a graph, right? Just like that other equation on movie tickets and such. So 2 comma negative 3 is a point. Now this next one says, here's your new f of x equation, y equals this. It says find the value of x for which f of x equals 12, or for which y equals 12. So now we're not doing f of 12, we're not substituting 12 for x, we're substituting 12 for y, and we're finding the value of x that makes that so. I mean, they literally said find the value of x, so we can't make that mistake. But we're solving for x this time, our input based on our output. They're dividing both sides by 4, and they get x equals 3. So you get an output of 12 when x equals 3, and that's the answer. So it looks like they're going to be doing a lot of those kinds of problems here, at least it appears. The first two, numbers 8 and 9, we have to do 3 different sets of inputs. We have this function, f of x equals x plus 8. And it looks like based off the instruction, we have to find f of negative 3, f of 0, and f of 5. So 3 different substitutions into here. F of negative 3, which is negative 3 plus 8, or 5. There's one of them. F of 0 is 0 plus 8. Notice I'm substituting for x, and that's 8. And f of 5 is 5 plus 8, which is 13. Now, it's one of the easier versions of substitution that you can do, and as well as pretty much any linear function, but those are the 3 that you're doing when x is negative 3, y is 5, when x is 0, y is 8, and when x is 5, y is 13. Number 9, we have, doesn't look like exactly slope-intercept form, y equals mx plus b, but we didn't know that one yet. We knew y equals mx plus b, but we didn't gather its purpose, so I'm going to leave it exactly like this, 4 minus 3x. And let's do f of negative 3 by doing 4 minus 3 times negative 3. Negative 3 times negative 3 is positive 9, and 4 plus 9 is 13. So when I substitute negative 3 for x, I get 13 for y. Let's split these ones up like this. When I substitute 0 for x, I get 4 minus 3 times 0, which of course is just 4. And when I substitute 5 for x, I get 4 minus 3 times 5, or 4 minus 15, which is negative 11. So for this different equation, we have these points on those ones. Numbers 10 and 11, we are now substituting a y value and finding the x value that associates with it. So on number 10, we have a k of x equation. It's still a form of y equals 7x. And we want to know what x is when y is 9, or 49, excuse me, is 49. So we're going to substitute 49 for y. Mr. Robinson, that says k of x. I mean, it means y. You know, that's the point. That's the point I'm trying to make when I'm saying y equals. I want to make sure you're aware of that. Divide both sides by 7. We're going to get an x value of 7. So x is 7 when y is 49, or y is 49 when x is 7, what have you. And that would be number 10. I mean, these aren't things you've done before as far as substituting. We're just making sure we understand what function notation is representing. I think that's really the whole goal. The algebra and the calculations, order of operations, those are all the easy stuff. They're just testing you on, do you know your function notation? And remember, this stuff is exercised more and more to the extent that they could ask these questions on the chapter test portion, but I assume that we're going to use these more when we do the later sections of things. Now, r of x equals 19. 19 will substitute right into here, and we're going to solve for x. This time I'm going to turn the x terms positive by adding 5x over, in which case I'll subtract 19 over. And I get 5x equals negative 20. As I divide by 5, we get x equals negative 4. Negative 4 is our input. 19 is our output for that equation. Okay, numbers 12 and 13 say graph the linear function. Now, I do want you to be aware that this was during a time in a section, which may or may not work for what I want to state. But if this were instruction, if this were an instruction without the actual section in mind, I would just graph using slope-intercept form. After all, these are in slope-intercept form. However, because we are in section 3.3, let's go ahead and practice table usage, function notation, substitute values in, and get values out so you're well aware of what you can do, case you don't know slope-intercept form, in case that's not in slope-intercept form, we want to know that we can always graph using a table when we want to. Okay, that's kind of the idea. So here's what I'm going to do. I'm going to make a table of values. I like to default some negative, some positive, and 0. And for the case of these values, it'll make most sense to use -2 up to 2. Like, don't get too extreme with them because you can't multiply 2 by like 7 and get something that is small enough to still fit within this window range. So these will be fine. Now my y, I wrote y here, but I also could have written g of x, and I probably want to do that here. Let's do x and g of x to say that's still y. I want to find g of -2. That's -2 times -2, which is 4, minus 3 is 1. That means there's a point on my graph, which is -2, 1. G of -1 is -2 times -1, which is 2, minus 3 is -1. So -1, -1 is a point. G of 0 will be -3. This term basically wipes out there, and that's something to remind ourselves of. That wipes out, and you get -3 on that. G of 1 is -2 times 1. -2 minus 3 is -5. And G of 2 is -2 times 2, which is -4. Minus 3 is -7. Now, I will graph based off of just these 5 points only. But I want to see now, when you look at this graph, you'll say, okay, does this graph agree with what you know about graphing on a slope-intercept form? Number 1. Number 2, can you now recognize through table form? Because we might have skipped, right? When we did slope-intercept form, we didn't look back at tables again. So can you look back at this table and say, oh, I understand why slope-intercept form says what it says and where the pattern comes from. The y-intercept here, the rate of change on y here, where we're subtracting 2, how these two numbers have to do here with what we have there. Hopefully you're kind of trying to, draw those connections. But of course, we used a table for this one just to get the graph going. And there it is. We do connect it, all real number domain. We draw arrows at the end of them. As you can see there, it continues both directions. Number 13, h of x equals 2/3 x plus 4. I'm going to do the same thing. I'm going to use a table. However, with this one, because it says 2/3, I'd like to substitute values that I can divide by 3. If I can divide them by 3, then I get nice clean numbers out, right? Integers. Fractions are not clean numbers. We all know this. Or decimals. They're no fun. We don't like those. So if we can fit some points within here, some negative, some positive, and 0, I'm all for it. Let's do x and y. Oh, pardon me. H of x. X and y. 0 will be in the middle. Sure, that's fine. I could even tell you that value is 4. We'll start off with that. But from here, what are multiples of 3? 3 and 6, those numbers can divide by 3, so -3 and -6 can also do the same. Let's go to the positives first to start, just not mess ourselves up early on. 3 times 2/3 is 3 divided by 3, which is 1, times 2 is 2, and 2 plus 4 is 6. So 3 6 is a point. 2/3 of 6 is, 4. 6 over 3, 2 times 2 is 4, plus 4 is 8. Maybe you see that increase in the change here, but this is specifically because x's are changing by 3, nothing more, nothing less. But let's try -3 here. That's -2 plus 4, which is 2. -6 is -4 plus 4, which is 0. And that seems to show as x increases by 3, y increases by 2. Where have I heard that before? Oh, yeah, a later section. But let's plot these as we see them. -3, 2. -6, 0. 3, 6. And 6, 8. Now, once again, when you look at these points, not only do they look linear, but do they look like that you would know how to graph them based off of what you see here? And do you understand where these numbers come from? I'll go back to them in just 1 second here, because we did bring them up, and I do want to make sure that we're connecting all the dots, that our processes are what they are for a reason, and the values that we skip and such. First of all, y-intercept. Second of all, change in x and change in y. Notice what these values are here specifically, how we're increasing by 2's on y as we increase by 3's on x. Almost as if every time we go up 2, we go right 3. Okay. All right, so those are our graphs. That is section 3.3 with function notation. I did technically do h of 3, h of 6, and things like that. So function notation, sure, that was used. All right, let's move on to section 3.4. This is where we use standard form. Now, once again, we might have done so much slope-intercept form recently that you might have forgotten how standard form works. This is where review comes great. So, on numbers 14 through 17, we are going to graph those equations. But before so, let's take a look at this equation that they want to graph. 2x plus 3y equals 6. Not quite slope-intercept form. No. Standard form is x and y on the same side of the equation. a constant on the other side, preferably all integer values. That's for the most part how these are going to work. And we want to get the intercepts of the graph. We talked about a y-intercept right here very, very quietly, that's a y-intercept. It's where we cross the y-axis. Well, here's the x-intercept, where it crosses the x-axis. The x-intercept is the value of x when y equals 0. After all, this is negative 6 comma 0, is it not? And this was 0 comma 4, the value of y when x equals 0. That's the y-intercept. Well, we can use this equation and find the x-intercept and the y-intercept by setting the other variable equal to 0. To find the x-intercept, substitute 0 for y and solve for x. And you'll notice what happens is this term goes away. 3 times 0 is 0. And then you have 2x equals 6. If you divide both sides by 2, you get x equals 3. That becomes your x-intercept of your graph. You can actually plot that point. Now the y-intercept, you set x equal to 0, so that term goes away. You have an equation that says 3y equals 6. When you divide both sides by 3, you get y equals 2. That's another point on your graph, the y-intercept. You only need 2 points to make a line. As much as we made 5 points for precision, or when we use slope-intercept form, I'm going to say plot as many points as you can fit. You can use 2 lines provided that your ruler is going to be enough to carry you through the rest of the way. So if you use some sort of straight edge here, connect these dots and draw an arrow through the rest of your window, I think we're going to be satisfied. So we're going to graph these equations by doing x and y intercept values, at least for numbers 14, 15. We'll talk 16, 17 in a bit. But for numbers 14, 15, we're going to be doing that. So I'll prepare the graph. And we first start with the equation 8x minus 4y equals 16. Now we got to the point on these ones where I was doing them mentally a little more so than not, but I will at least start with this. X-intercept, I set y equal to 0. That means this term goes away. My equation now says 8x equals 16. And if you divide both sides by 8, you will get x equals 2. So we have an x-intercept of 2, 0. This is where we cross the axis. The y-intercept, we set x equal to 0. So we do the same thing for this portion here. We hide this, but be careful. Don't hide it like that. Don't make it say 4y equals 16. 4y is a negative value. So be very careful there. Now, you don't want to cross things out. Just use your finger and hide the term. But this would say negative 4y equals 16. And I can divide both sides by negative 4. That'll be y equals negative 4. Remember, it will be a negative value. These 2 points alone can determine what line you have, and as long as you can draw a straight line through them, then you'll be good to go. I'll make sure to fix this because that is clearly not it. But draw a straight line through them, and that will be your graph for this particular equation. And it is linear, right? Just because it's in standard form doesn't mean it can't be linear like that. So I did the hiding method for that. Hide and divide is the way that I can say that. I know I've said that before, maybe not in the videos here. I can't say, hey, I just thought of that on the spot. But that's something that I started to say over time on these things here. I got to Google search that and see if anyone else has been saying that for these kinds of problems. Is that all we have to do? Yes. Number 15. Negative 12x minus 3y equals 36. So this time, let's try the x and y intercepts without use of, let's say, I don't know what I was going to say. Oh, without use of any actual kind of hiding and such. X-intercept, if I set y equal to 0, it'll say negative 12x equals 36. I got to divide 36 by that negative 12. I'm going to get negative 3 for x on that one. So it's right here. Now the y-intercept, I'll hide this x term, and it'll say negative 3y equals 36. That means I have to divide that one by negative 3, and I'll be getting y equals negative 12. Now this will not fit on my scaling perfectly. I'm just going to kind of makeshift it. I'll go 11, 12, and kind of fit it right down there. Sorry about that. We could change scales. I chose not to. I don't want to. And we have this line right here. So this is not your slope-intercept form y equals mx plus b. We are not using those numbers negative 12 and negative 3 specifically to determine, although these were just opposites of each other to get those. That was just happenstance. That doesn't always happen. So, you know, we did get our intercepts. We drew our graphs. We're all good to go. Now, numbers 16 and 17, they kind of have a standard form appearance, but they're missing a variable, which means we could get one of the intercepts. Like I know on y equals negative 5, I should have a y-intercept, well, of negative 5. But it's a little more than that. What kind of graph is this? We learned more once we hit section 3.5 on slope-intercept form. The fact that there is no x term there means the slope is 0, things like that, which is a good way of reminding ourselves that a slope of 0 is a horizontal line, and a y equals negative 5 equation is also a horizontal line. that we graph across y equals -5 literally like this, as if to say no matter what value we have for x, you don't have to plug it in, just no matter what x represents, y is always going to be -5. And no, just because y is an up and down thing doesn't mean we draw the line up and down. It means we bring our line down to -5 and we graph this thing left and right. So there's the y equals -5 equation. And x equals 6, therefore, this is the very reason why they're calling these linear equations and not linear functions, because x equals 6 is in fact not a function. If you heard what I stated before about the things that would make it a linear equation, we said we could write it in, y equals mx plus b form. This can't be written in y equals mx plus b form because one of the things I stated is the y term must exist. And I stated on 16, the x term doesn't need to exist, but here it must. That doesn't mean I can't graph it. It just means it's not a function. Why isn't it a function? Because it fails the vertical line test. How come? Because it is a vertical line. It's a vertical line at literally x equals 6. Here's the x-intercept, but x is always 6. No matter what y is, up and down on x equals 6. No matter what y is, x is always 6, and there is your line. Undefined slope, not a function, but it is a linear equation, and you can graph it. There's a vertical line there. Remember, just like, hey, y goes up and down. Why, hey, x goes left and right. Yes, we go right to 6. On the right to 6, and there's your graph. Okay. Mr. Robinson, I really want to show you that I can graph in y equals mx plus b form, slope-intercept form. I really want to use that review. Can I do that all the time? Maybe. I don't know. But we can do it here, graphing linear equations in slope-intercept form. They start with this equation, which is not in slope-intercept form. I'd even argue that it's not in standard form, despite the fact x and y are on the same side. That's a fraction. Standard form generally won't have fractions, though you can find the intercepts that way pretty quickly. But rewrite it in slope-intercept form by adding 1/2 x to both sides, and they do exactly that. Now this is y equals mx plus b form. Y equals mx plus b. M represents our slope. B represents our y-intercept. So the way that we want to do this graph is we start from our y-intercept of 0, 1. We plot that point there as a reference point because everything we do is in relation to that point there. You could plot any point on here, but we're trying to use these two numbers to construct our graph and nothing more to calculate. How do you use 1/2? It's actually really easy. In fact, fractions are preferred in these problems. How do you do that? You rise 1, you run 2, you plot another point. And I've been kind of showing, or you can run 2, rise 1. Whichever way you want to say it, you should end up at this destination right here. Rise 1 again, run 2 again. This is a positive slope. Both 1 and 2 are positive. We go up and we go right. But you can also go down and left. Mr. Robinson, those are negative. Yes, but -1 divided by -2 is still positive 1/2, baby. That's still a positive slope. So this continues it. I'm going to ask you to plot as many points as you can fit for the graphs that we do. Or I'm going to do that. So this is as much as they could fit, and they draw their line with arrows, that kind of thing. Pretty easy thing to do, but it doesn't indicate what it is unless you're in slope-intercept form. They do ask to identify the x-intercept. I still don't know what that ultimate goal is besides word problem usage. I guess they're just making sure that you know what x-intercepts are and that what we're plotting is not the x-intercept to begin with. We plot the y-intercept. So it crosses the x-axis at -2, 0, so the x-intercept is -2. Okay, let's do numbers 18 through 20 where we do graph and identify the x-intercept. Because we're in this section, we will put it in slope-intercept form before we do any of the graphing. So y equals 2x plus 4 is already in y equals mx plus b form. Now, I'm going to identify the slope for you as a fraction because I want to talk its rise over run. It's 2 over 1. The b is a y-intercept of 4, so I'm going to identify it as an order pair 0, 4 to again remind ourselves where we're beginning our plotting. So for this graph here, we do have a starting point of 0, 4, and the up 2 over 1 portion applies. We don't just rise 2, and we definitely don't rise 2, run 2. It's rise 2, run 1. The larger the slope value, the steeper the line will become. So if this was 6 or something like that, it would be significantly steeper. Now I'm also going to go down and left, just like I mentioned in the example problem, to fill out this graph and continue the process of the slope as it has an all real number domain and apparently an all real number range. But here is the equation for this graph. We just plotted about 10 points together, something like that, 11 points together without using a table. If we use the table, that would have taken significantly longer to do. So there's a nice steadfast way of tableless graphing that. Then again, we could have also done some standard form deals. And, when I look at numbers 19 and 20, which are in standard form. Oh, by the way, before I actually move on to number 19, let's talk about x-intercept. The x-intercept here was negative 2. So on numbers 19 and 20, listen, they're they're in standard form. We just came off standard form. Should we graph out of it? Well, we're in this section on slope-intercept form, so probably not. But the fact is, you could as well, right? I could divide these by 5 to get the x-intercept. That is my y-intercept right there, you know, things like that. But let's get it in slope-intercept form. Let's add 5x to both sides. We did standard form. It's done. It's taken care of. We have 5x minus 10. And here's the thing, guys. Remember, in the chapter test, if they don't force a form on us, I'll probably graph out of the form it's in. Standard form will be of most use for me if my intercepts are not fractions. So as long as they're not fractions and it's in standard form on the chapter test, I'll graph out of standard form. If it's in slope-intercept form, or standard form will lead me to fractions and such, I'll graph out of slope-intercept form. It just depends. Anyway, we're y equals 5x minus 10, where our slope is now 5 over 1, and our y-intercept is 0, negative 10. I did mention the y-intercept would be negative 10, and there it is. So we're starting all the way down here, and we get to rise 5 and run 1. Very steep graph, even in comparison to the last one with the slope of 2. We're going to have to look at maybe some fraction ones in a bit, to look at something less steep. We still have to look at a negative slope. We have not yet run across one. Because these are all positive slopes, right? They go up as they go right. Negative slopes would go down as they go right, and we'll see if we run into one on number 20. Now this has an x-intercept of 2. And then we're finished with the problem. Okay. Number 20 says x plus 3y equals 9. If you consider what standard form would require for you to do to graph this, we would get those 2 points for the x-intercept, which I see clear as day, and the y-intercept by dividing by 3. It's not a lot of work. I'd say standard form is the better way to go for a problem like this. But we're in slope-intercept form territory right now, right? So you're like, I like slope-intercept form. Okay, well, here's what you'd have to do. You'd have to solve for y. Subtract x from both sides like this. Now the equation says 3y equals negative x plus 9. Get that x term first. And then divide everything by 3. Now this negative x over 3, you want to clearly see what that m term is, what that slope is. So you might want to rewrite this as negative 1/3. That's negative 1/3 x and then plus 3. So now we have our equation that's in slope-intercept form. That's like multiple steps in reperception of this x term for this to be slope-intercept form. And now you still have to graph it. Now the slope's negative 1/3. Not x, but just negative 1/3. The y-intercept is 0, 3. So I'm going to start at 0, 3 right here. And by the way, when I do, if I do the chapter test and I graph out a slope-intercept form or whatever, I'm not going to be writing this information down anymore. I'll call it out, but the writing stuff is just assistance. I'm going to start at 0, 3, and because it's a negative 1/3, we go down as we go right. It's going to look more like this here. So I go down 1 as I go right 3. As you can tell, the number's already a fraction, and this is just a nice way of going about it. Fractions are nice for slopes. It's a pretty easy count, but then I'll also go up 1, left 3. So here's the negative slope I was looking for. Here's the fraction slope I was looking for. Looks like this review is covering a lot of things that we wanted to try and do. And so this will be our line here. Now they will ask for x-intercept, and it does cross the x-axis all the way down here at x equals 9. So we have an x-intercept of 9. Of course, I could have told you that right here. Set y equal to 0, x equals 9. And y-intercept would have been 3. Divide these by 3, and I would have been able to graph out a standard form. I think graphing out a standard form would have been significantly faster there. As much as people are going to love slope-intercept form, understand why standard form will be better in certain cases. And I think that's one of them. That's okay. This is good practice. I wanted to do that. Okay, number 21. A linear function h models a relationship in which the dependent variable decreases 2 units for every 3 units the independent variable increases. So they're giving you some words to describe out what's happening for the situation. It sounds like what they gave us was a slope. The dependent variable, the y, decreases 2 units. For every 3 units, the independent variable x increases. That's positive. It says graph h when h of 0 equals 2. If h of 0 equals 2, that's your input of 0 for x, your output of 0 for y is a point 0, 2. That means that's your y-intercept. Your y-intercept value will be 2. So they're saying, well, they're saying graph it. What did they say? Write it? Okay, they never said write the equation. I'm going to want to do that. So my equation will be h of x equals, because they did call it h, not y. Your slope is negative 2/3, so negative 2/3 x plus 2. You know what I haven't mentioned? I've been mentioning quite a bit that you don't call your slope the thing with the x on it, right? That it's not this x. That would be incorrect to state. You know what I didn't mention before? A lot of people forget to write x here sometimes. It sounds weird. It sounds weird, but a lot of people forget to write that, especially when you get so focused on what is my slope and I need to write my equation. If you get to include the x there, that's what makes y change. That's what makes y change based on plugging in different values for x. Otherwise, negative 2/3 plus 2 is 4/3, and that's it. Y equals 4/3. Have fun graphing that horizontal line. No, this is this one. Y decreases by 2 every time x increases by 3. Don't forget that x to multiply with negative 2/3. Anyway, hey guys, it's slope-intercept form. They're going to ask us to graph it, identify the slope, y-intercept, and x-intercept of the graph. Okay, we have the slope. We have the y-intercept of these things. Let's sketch this graph. We are in our slope-intercept form section, so I will use this as we have been. So y equals negative 2/3 x plus 2, where we now have, hold on, I can grow this. I'm not doing anything else here other than x-intercept. So we have 2 as our y-intercept. We go down 2 as we go right 3. It looks like that's our x-intercept there of 3. And we go up 2, left 3 as well. Complete the graph. So there's our graph. We have our slope and our y-intercept, and now we have our x-intercept of 3. Now, if there's ever a time where on our graphs and they ask you to identify that your x-intercept is either out of your window range or domain, or it's a fraction, you can always set y equal to 0, not h of 0, but make it say 0 equals this and then solve for x. If I solve for x here, I would actually get 3. But I'm just stating in that instance there, if it was a weird fraction or something, you could do that. Okay. 4 to 7 minutes in, I want to state that some of you guys haven't done section 3.6 before. If this is your first time doing it, I'm not going to slow down that much on it. I did want to say some of you guys might be out of here, in which case, awesome. I'll see you next time. But for the rest of you guys staying for the last 7 problems, let's take a look at what's going on. They are giving you an example of how we can graph f of x equals x. Well, that's just 1x. And by the way, I should just mention that. That's y equals 1x plus 0, where if you can't see the y-intercept, that means the y-intercept is 0. If you can't see the slope, that means the slope is 1. So this graph is a y-intercept of 0 and up 1 over 1 kind of slope. As much as the review did for us in a lot of different ways of complex problems, it didn't do the most basic problem. It is now, but it didn't do the most basic problem, and that might be the one that you fumble with the most. So anyway, there's that function, and that's known as a parent function because it has 0 transformations applied to it. No translations, no shifts, no stretches, no reflections, whereas g of x totally does, negative 3x minus 2. Now, negative 3x minus 2 is this red one right here. They have a blue one and green one right here. We'll talk about what those two things are as we start to transform, going from f to g. So they say describe the transformation from the graph. So a few things are happening here. You have a 3 multiplying by x, and the 3 is negative. When the 3 is multiplied by x, you have this blue equation here, where the black turns to blue by making every y value 3 times more than it was before. Now, do we have to do all those graph things? I don't know. I haven't been. I think I did it for one of the problems and I stopped. But we're going from this point here to now 3 times taller, and this point here to now 3 times, well, lower, but it's still a bigger number. Negative 1 times 3 is negative 3. These are known by these are known as vertical stretches. We're vertically stretching our graph by a factor of 3. By a factor of 3. Now the blue turns to green. What happened there? Well, it flipped over. In which way did it flip over? I guess I could say yes, it did. It could flip either over the x-axis or over the y-axis, and you'd get the same graph because this is still at the origin. They said the x-axis. I feel it that way as well. We're making our y values negative, so we're flipping over this axis right here, going like that. So, for example, this blue right here is turning into, say, this green point right there, and it's flipping over this axis. So that's known as a reflection in the x-axis. And the last thing we do is a translation of this thing. This minus 2 is taking your graph, and it's shifting all your points 2 units down. So we go from green to red. not just moving over like that. No, we're going from, say, this point right here to 2 units down right there. Or we're going from this point right here to 2 units down right there. And we're getting those new points, so the red is that equation. Now, I'm probably likely, as I explain that, just going to be graphing these things as they are, or taking what they have so I can make the graph, and then we can do some explanations after that. So that's our equation, that's our description. So we talked about vertical stretch by a factor of 3, a reflection in the x-axis, and a translation 2 units down. We could also do horizontal changes. We can horizontally stretch and shrink. We can horizontally translate. Now those ones are trickier and horizontally reflect across the y-axis. Those first two are trickier because we're going to see inside of the function, first of all, and second of all, it's going to be opposite of what we would normally do. You'll see what I mean when we do the problems. On number 22, we're going to for all these problems, we're going to let f of x equal 3x plus 4. Okay, this is for every single one of these problems. So we actually might live on this set for a while. So let me do this before actually starting number 22, okay? I'm going to have f of x equals 3x plus 4. Let's sketch that graph. And then let's use this graph for every problem that we do, just kind of copying and pasting it over, okay? So f of x equals 3x plus 4 is going to look like this. We've got a y-intercept of 4. We're going to rise 3, run 1, and fall 3, run 1 to the left. So this is using my slope-intercept form to get this graph done pretty quickly. Like so, like so. All right, there's this graph. We're basically going to lock this whole thing in, okay? We're going to use this for the next 6 questions that we have, this particular appearance of this graph. Ooh, that looks a little weird when it locked in. Did you see how that changed? I don't know how to make that look any better. Let's see. Lock it in. Okay, we'll keep it like that. So I'll keep this one off to the side as well. Okay, see, this happened when I was doing 3.6 at the time. I hit the copy button and it's not registering what I copied. There it is. Okay, I'm going to keep that off to the side, and there's this one we're going to use forevermore. So on number 22, in number 22, we're going to do a graph h alongside of it, and I have h of x equals f of x plus 3. We're going to describe the transformation from the graph of f to the graph of h. I'd like to do the description first in this case and kind of show you how everything pans out to be exactly as we described. So this f of x plus 3, the official thing we're looking compared to is f of x minus h. And this looks weird because this is a minus h but a plus 3, which means we're subtracting a negative 3. You change this to a negative 3. Don't actually change it to a negative 3, but you flip the sign of this, and that's the thing that we're doing to this graph. Because it's inside the function and it's adding or subtracting, that's a translation, and it's a horizontal translation. So again, this will make more sense if you did the section with me at the time. But we are or some people won't know how to. But the graph of h is a translation. 3 units left, not right. 3 units left from f. Now, that's what we're going to do with it. So, keeping that in mind, when we have this graph here, let's take that graph and let's translate that graph 3 units to the left. And it would look like this here. I'll have this same graph right here, like so. And let's translate that 1, 2, 3 units to the left. I was really looking at this y-intercept value, and I was going 1, 2, 3 units to the left. This is what our new graph would actually look like right here. This will be our h of x equation, whereas this is our f of x equation. Now, how can I tell that this is right? Because you probably looked at this and you said, wait, that doesn't look like our example. Our example had an actual equation that I could find the slope and y-intercept. What the heck is this thing? Well, let's make an equation out of it. You know what f of x plus 3 means? It means take your f of x equation right here and turn x into x plus 3. So it says 3x plus 4. H of x will be 3 times x plus 4, but its x will be x plus 3. So we get to distribute the 3 into here. 3 times x is 3x, 3 times 3 is 9, and 9 plus 4 is 13. You get 3x plus 13 as your equation. This is what that equation is right there. Now, is that equation? The weird part is 13 is our y-intercept. Listen, our slope is 3. I think we can agree that we're rising 3, running 1 like we did before. It's very parallel. But this y-intercept is 13. I don't see it hit 13. Well, if you go far enough, I think we can make sense of the fact it will. After all, right here it's at the point -1, 10. So when I go over 1 to 0 on x, I'm going to go up 3, 11, 12, 13. I think it does make sense that there it is. And I think it makes sense that we did this as a transformation first, so we could identify with the fact that, well, if I can't graph it on my own, I'm going to have to find means of doing it myself, use the transformation. So it's a translation, 3 units to the left, and there is the graph. Okay, let's go to number 23. I have to copy and paste that graph. But number 23, we have h of x equals f of x plus 1. Now this one has the plus 1 on the outside of the function, like that. That means we're affecting our y values in a certain way. So we can probably take what we just saw in the last one, where, remember, f of x, by the way, I need to write this again. I think it was 3x plus 4. What we're going to do on this one for our h of x is we can substitute 3x plus 4 from f of x, boom, and the plus 1 sits on the outside of it. We take our f of x graph and we add 1 to it. 4 plus 1 is 5. We basically turn the y-intercept from a 4 into a 5. So it's right here instead of where it was. So let's just graph this as it is, and let's see if we can understand what that transformation appears as. It's going to end up looking right next to this each time, where at every value that we were at before, we're now just 1 above it. If we're just 1 above it, that sounds like a translation of being 1 unit above it. So this graph here will be, blue, hold on. It's very tight with it, but if you consider at the same x values, you have a y value that's just 1 above it. This is a translation 1 unit up. A translation 1 unit up. The graph of h is a translation 1 unit up from f. Now, we could have described that from the beginning, right? This is some sort of f of x plus k when you start learning some of these letters here, because these letters are going to continue forward in whatever we do. It doesn't matter what the letter is. It matters how it's affecting your function, and it's adding to it, which means it's affecting your y values this time. Number 24 is h of x equals f of negative x. Now, the negative is inside the function, which means it affects something horizontally. The last time that we saw something negative was in the example question right here, and that affected it vertically. We reflected over the x-axis. We affected your y values. We made your y values negative. Now we're going to make our x values opposite of what they were. H of x is f of negative x. This means a reflection in the y-axis. So I'm going to write it first, see if we can do that reflection, and see if it makes sense. The graph of h is a reflection in the y-axis from f. Now when we sketch this graph of the original f of x equation, f of negative x will take that and it'll reflect across this guy right here that I'm going to draw in green. We're going to flip over this axis here. Think of this as a mirror. Whoops. Think of this thing as a mirror right there. So now, instead of going left or right 1 to go up 3, we're going to go left 1 to go up 3. But from this same y-intercept, left 1 up 3, up 3, left 1 like that, kind of like a negative slope. And we're going to see why this slope is negative based off of this being a reflection when we do the official transformation from the graph itself. So when I draw this line, let's first agree that what I did was a true reflection of this thing, because that's how this thing would work, reflection in the y-axis. And there's a difference between reflection in the y-axis and reflection in the x-axis for a problem like this, right? Reflection in the x-axis would turn the y-intercept negative, and then we'd go down like that. The x-intercept would stay the same. Let's take a look at that equation as a whole. Remember, it was 3x plus 4, so now it's going to be 3 times negative x plus 4, because negative x is going to substitute for x in our equation. And what's 3 times negative x? Negative 3x, which goes to show that was a negative slope, and that's what we needed out of that. Now, it looks like I slipped up a little bit here, because number 25 is exactly what I stated this other one's going to be, negative f of x. So h of x equals negative f of x is going to be a reflection in the x-axis. Now, the difference in appearance will be kind of what I stated, exactly what I stated. It'll flip over the x-axis, means the y values are going to turn negative. That means things like the y-intercept will change sign. Instead of being a positive 4, this will be a negative 4. Instead of being at this point at 1, 7, it'll be at 1, negative 7. And you can see this will have that slope of 3, or negative 3. And we'll continue on this path, and it'll have the same x-intercept this time, because when x is whatever the x-intercept is the value of x and y equals 0. And when y equals 0, if you multiply it by 3 or by negative 1, it's still 0. So that doesn't change anything. Therefore, these x-intercepts are the same because now we're reflecting across this line instead. This graph is a reflection in the x-axis, just like what you saw from the example question. The graph of h is a reflection in the x-axis from f. Now, if we go back to our equation thing, you'll say, Mr. Robinson, isn't making your y value thing negative the same thing as just the last one, negative 3x plus 4? Not quite, because we're taking the entire f of x equation of 3x plus 4 and making it negative. That means we distribute the negative into both terms. So this equation will now say h of x equals negative 3x minus 4. And that's the big difference here. A y-intercept of negative 4 instead of positive 4 is indeed a reflection in the x-axis. Past the hour mark, so that means our timestamps are going to have to reflect that as well. Still 3 more problems to do. We have some stretches to take care of, perhaps. So number 26, we have h of x equals 3 times f of x. Now we saw what a 3 does from up above previously, although there was also a reflection. They mentioned it, a vertical stretch by a factor of 3. That means everything's 3 times larger than it would have been before. You just saw what happened when we made f of x negative, the negative distributed on the outside. So let's try that same thing here, and let's distribute the 3 on the outside of 3x plus 4, and it's plus 4 there, and distributing the 3 will become 9x plus 12, excuse me, 9x plus 12. So kind of an interesting one, even when it comes to graphing, because we can describe it with that vertical stretch all we want, but that's hard for me to manipulate this graph for myself. It'll be hard for you because you don't have computer software to make your graph. So how do we do that? 9x plus 12, 11, 12 is all the way up here. It's possible to do this and count down 9 over 1 if you know that 12 minus 9 is 3, and then 1 over here. It takes a little bit to do. Notice that I have to go down, and I'm going left to keep it positive. But here's what else we could do. Substitute a value for x, man. Do a negative value. Let's try negative 2, see where it goes. 9 times negative 2 plus 12 is negative 18 plus 12, which is negative 6. That means there's a point on our graph that's negative 2, negative 6. It's this guy right here. Now, from this point, you can do your slope of 9. I clearly can't go down and up over anymore, but I could go up 9, and guess where I'd land? Right here. Up 9 over 1 and up 9 over 1. So just plot what you can fit, right? Sometimes if you can't fit your points, listen, I could have changed my scale, but sometimes if you can't fit your points, plug in an x value that will fit within your window range and go from there, or do some counting without the counting, right? What's 9 down from 12? It's 3. That's a subtraction. So there are things you can do to change it, and there it is. So this graph, notice it has the same x-intercept, by the way, just like the other one with the reflection. We are vertically stretching this by a factor of 3. Everything got 3 times taller, including the y-intercept, including the slope. So the graph of g is a vertical stretch by a factor of 3 from f. Last one of this set, and then we'll see what that final problem is. It says h of x equals f of 6x. Now, they saved this one for last, and it is the hardest one to kind of discuss, but we'll get it done in short order if we can. H of x equals f of 6x. This is inside the function. That means it's a horizontal change, but just like the horizontal translation being opposite of what you do, because this is multiplying by 6, your x's are actually needing to be 6 times smaller to compensate for the fact they're about to be 6 times bigger to match the same y's as these ones will be, or as the original ones would have been. So we don't say a horizontal stretch by a factor of 6. We say a horizontal shrink or horizontal compression by a factor of 6. The graph of h is a horizontal shrink by a factor of 6 from f. So let's do this. Let's look at, and by the way, there were other things I could have done with that last graph based on stretches if I did one point at a time, but there were so few points to do it from. Let's see if we have any points to do this one with as well. We have to, by a factor of 1/6, they'll say, not 6. 1/6. We're going to take our numbers and divide it by 6, and that looks to be a problem based off this graph here. Look at your x values here. This is when x is 0. 0 divided by 6 is still 0, so the y-intercept will stay the same. This is when x is 1. 1 divided by 6 is 1/6. And this is hard to plot, but basically I have a point that's right there. The same height, but now it's 1/6 of the way from the y-axis. And this is 2 divided by 6, which is 1/3. This will be a very skinny graph. And this is one of those graphs that I very much shame them for using. I wish they did a stretch of some sort to let us work this out, because this is going to be a tiny graph. And I'm going to show you how this thing's going to change in the overall scheme of the problem. This 1 divided by 6 is also 1/6. This 2 divided by 6 is also 1/3. This 3 divided by 6 is 1/2, negative 1/2. 4 divided by 6 is 2/3. And look how skinny this graph will be. See, there's not much I can do with that unless I change the scale of my graph. That's not my plan. So here, h of x, remember f of x was 3x plus 4. So now we have to do 3 times this plus 4. 3 times 6x plus 4. You know what our slope is here, guys? It's 18. It's 18. This is our graph. We start at 4 and we go up 18 over 1. I can't fit that. We go down 18 over 1. I can't fit that. It would go down to negative 14 before I can even actually plot the point. It'd be all the way down here to get that integer. So this is kind of a weird graph. This isn't just the fact it's a horizontal compression. They made this graph extremely skinny. And it's not the first time that they've done it on problems like, well, it's the first time they've done it in an IM1 problem. But IM3, IM2 problems like that, they've done it a few times, man. They're very interested in making these quite the bizarre looking problems. There's the answer. I'm going to leave it at that, and that's part of your review. So if only we don't do it on the chapter test as well, I'll feel better. The last question we have is number 28. Says graph these two things and describe the transformation. Oh, this is no different from what we just had. I mean, it's different because it's a different function here, but it's the same kind of stuff, same instructions. So f of x equals x, and then g of x equals 5x plus 1. If we were to describe first in full, understand because this parent function's straight up x, it'll be a lot easier to see what's happening. I can see what's happening. It's multiplied by 5 and added with 1. There's the translation that, I don't know. We're multiplying by 5, then we're adding 1. These are both vertical changes as they're affecting your y values. X gets multiplied by 5 plus 1, you get y. So the graph of g, this is a combination of transformations, by the way, is a vertical stretch by a factor of 5. I guess this is a lot more like the example question. By a factor of 5 from f, followed by a translation 1 unit up. Now, I fully plan on just graphing these two things here together. I'll even give you an in-between graph of the vertical stretch, kind of like the problem did in the book. But after that, that'll be all she wrote. No, I totally did not copy that graph. Please, please, please. All right, I'm just going to bring this graph over. Like, please, please, please honor my request. This has been happening a lot more lately than not. Okay, so f of x equals x. Again, that's y equals 1x plus 0. So it's a y-intercept of 0 and a slope of 1 like this. So here's the original parent function. I'm going to graph the other one based off, you know what? Let's do this. Let's do it the way the example did, which is not graph 5x plus 1, but graph the vertical stretch and then apply the translation. So here's how I'm going to do the vertical stretch. I'm going to make everything 5 times taller in y business. 0 times 5 is 0. 1 times 5 is 5. 2 times 5 is 10. Negative 1 times 5 is negative 5. Negative 2 times 5 is negative 10. I have now vertically stretched my graph by a factor of 5. I haven't done the translation yet, but I vertically stretched it by a factor of 5. Now what I'm going to do is take that graph and I'm going to translate it 1 unit upward. Translating this 1 unit upward, I'll do in green at the very end here. We'll take this graph and we'll go up 1 unit, boom, like that. And there's my new graph. I'm going to try and differentiate them, give themselves a little more space. So there, boom. So that's g of x equals 5x plus 1. Notice it has a y-intercept of 1 right there, and it goes up 1, or up 5 over 1, up 5 over 1 like that, and down 5 over 1, and whoops, down 5 over 1, and down 5 over 1 like that. So I tried to kind of fit them the right way. We'll see if that was proper. But that is that last graph after all said and done, and we're finished. Guys, that's the end of it. That ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. You can tell how Section 3.6 is its own thing, and they definitely overcrowded it in my book. They had a lot to cover. I get it. We had to hit these reflections, these translations, things like that. But the chapter's focus to me is not about that. If the main takeaways for me are the stuff on vocab, what's a function, what's linear, things like that, and then graphing out a standard form, slope, intercept form. And look, we got to do slope-intercept form graphs, a whole bunch of them at the end there. I hope it was very good. So upcoming will be the chapter test and cumulative assessment. I hope you're ready for those ones. Take care, guys. I'm going to see you in that next one.